1885. A Kansas dirt road. J.D. Adams watches his horse-drawn blade scraper create another uneven mess. The blade can't hold an angle, it can't follow a curve. Every pass leaves ridges and valleys that turn to mud trenches when it rains. Adams knows there has to be a better way. What he doesn't know yet is that he's about to invent the machine that will grade every road, runway, and railbed in America. A machine so precise that 140 years later, operators will guide it to tolerances measured in millimeters, and so difficult to master that veteran heavy equipment operators call it the violin of construction machinery. This is the story of how a simple horse-drawn blade became the most precise machine on any construction site, and why, even in an age of GPS and artificial intelligence, nobody has figured out how to replace the human sitting in the cab. The problem was everywhere in the 1880s. America was building roads, rail lines, and canals at an unprecedented pace. Grading, creating a smooth, level, properly sloped surface, separated success from disaster. A poorly graded road would wash out in the first heavy rain. A poorly graded railbed would derail trains. But the tools available were primitive, horse-drawn scrapers that moved dirt but couldn't control slope, angle, or crown. Every road crew had men with shovels making final adjustments by hand. It was slow, it was imprecise, and it was about to change. J.D. Adams ran a road construction company in Indianapolis. He'd spent years watching crews struggle with conventional scrapers. These primitive tools consisted of little more than a steel blade dragged behind horses. The blade couldn't tilt, it couldn't angle. Every change in terrain required stopping the team, manually adjusting wooden blocks under the blade, and starting again. A single mile of road might require 50 stops for adjustments. The process was maddeningly inefficient. The breakthrough came when Adams realized the blade itself needed to articulate, to tilt, angle, and rotate independently of the wheels. In 1885, he patented the Little Wonder grader. The innovation was deceptively simple: a blade mounted on a frame that could be adjusted from the operator's seat using a series of levers and gears. The blade could tilt to cut a crown into a road. It could angle to push material to one side. Most importantly, it could be adjusted while moving, so the operator sat exposed on a metal seat, pulling levers that controlled the blade through a mechanical linkage of gears, chains, and pivots. Each lever required significant physical effort. There was no power assist, just mechanical advantage. But it worked. Suddenly, one man with horses could do the work of 12 men with shovels and do it more accurately. The Little Wonder weighed approximately 800 pounds without the horses. The blade was 8 feet wide, made from high-carbon steel that could hold an edge through a full day of cutting. The frame was wrought iron, built to withstand the constant vibration and shock loading from rocks and roots. Adams sold them for $250, roughly $8,000 in today's currency. Road contractors bought them as fast as Adams could manufacture them. By 1890, horse-drawn graders had become standard equipment on every significant road project in America. Adams didn't stop there. His next innovation became legendary among road builders: the leaning wheel grader. Traditional wheels ran parallel. Adams designed wheels that could lean inward like a motorcycle in a turn. This allowed the machine to work on steep side slopes without tipping over. A conventional grader would slide sideways on a 30-degree slope. The leaning wheel grader could hold a line on a 45-degree slope while cutting a drainage ditch or shaping an embankment. It was the first machine that could follow the contours of natural terrain instead of fighting them. By 1900, horse-drawn graders were ubiquitous on American road projects. They were pulled by teams of 4 to 8 horses depending on soil conditions. When the operator sat on a steel seat exposed to sun, wind, and dust, controlling the blade position through a maze of levers and wheels. It required constant adjustment: lift the blade for a rock, angle it for a curve, crown it for drainage. Good operators developed an almost musical sense of rhythm. Blade down, cut, lift, shift, drop, cut again. The blade sang as it scraped through packed earth, a high metallic whine that veteran operators could read like an instrument. Too high-pitched meant the blade was skipping. Too low meant it was digging too deep and would bog down the horses. But horses had limits. They tired. They couldn't pull through wet clay or compacted gravel. And they couldn't generate the sustained power needed for large-scale road building. As America entered the 1920s, the automobile age demanded better roads. ESA and better roads demanded more powerful graders. The machine was about to get an engine. The transformation happened in stages. Early attempts simply replaced horses with tractors. A tractor pulled the same horse-drawn grader frame. This added power, but didn't solve the fundamental problem. The operator still sat on the grader, disconnected from the power source, unable to coordinate blade adjustments with forward motion. Caterpillar engineer Clyde Cole saw the answer: integrate everything. Put the engine, the blade, and the operator on a single articulated frame. give the operator direct control over both movement and grading. In 1931, Caterpillar released the Auto Patrol, the first true self-propelled motor grader. The machine featured a gasoline engine mounted at the rear, producing 50 horsepower, modest by today's standards, but revolutionary for 1931. The engine drove the rear wheels through a mechanical transmission with 4 forward speeds and 1 reverse. A blade assembly sat in the middle of a 20-foot wheelbase. An enclosed cab at the front protected the operator from dust and weather, a luxury compared to the exposed seats of horse-drawn graders. For the first time, the operator could control ground speed, blade angle, blade tilt, and blade height from a single position. The controls were entirely mechanical: steel cables, levers, and rods connecting the cab to hydraulic cylinders that moved the blade. The Auto Patrol could grade at walking speed or reach a top speed of 15 miles per hour on hard roads. It could work through wet soil that would have exhausted a horse team in minutes. Most importantly, it could maintain consistent speed and blade pressure regardless of material resistance, something horses could never do. And it introduced a feature that would become iconic: the circle. The circle is the genius of a motor grader. It's a massive ring gear that surrounds the blade assembly like a hula hoop, allowing the blade to rotate 360 degrees. The blade isn't rigidly attached to the frame. It's mounted on this circle, which is itself mounted on the frame by a drawbar. This means the blade can rotate completely around while the frame stays pointed forward. An operator can cut a vertical face on the left side of the road while the machine moves straight ahead. The circle can be tilted to create complex compound slopes. The blade can be angled forward or backward to control how aggressively it cuts. Every adjustment changes how the blade interacts with the material. Understanding the circle requires understanding what a grader does that's different from every other earth-moving machine. A bulldozer pushes, an excavator digs, a scraper scoops, a grader sculpts. The blade doesn't push material away. It shaves it off in thin layers and redistributes it precisely. A skilled operator doesn't just move dirt. They create mathematical surfaces: parabolic road crowns, consistent 3% slopes, perfectly flat rail beds. The circle gives them infinite blade positions to achieve any surface geometry. But infinite possibilities require infinite judgment. This is why operating a motor grader is considered the pinnacle of heavy equipment skill. A new operator can learn a bulldozer in a week: forward, backward, blade up, blade down. They can run an excavator competently in a month: dig, swing, dump, repeat. A grader takes years to master. Some say 5 years minimum before you're truly proficient. The challenge isn't physical. Modern graders have power steering and hydraulic controls that respond to fingertip pressure. The challenge is mental. You're simultaneously controlling forward speed, blade height, blade angle, blade tilt, circle rotation, articulated frame steering, and wheel lean. Each control affects the others. Change your speed, and you must adjust blade angle to maintain cutting depth. Tilt the blade, and you must compensate with circle rotation to keep the cutting edge aligned. Turn the articulated frame, and you must adjust wheel lean to prevent the blade from digging in. You're reading the material ahead. Clay cuts differently than gravel. Wet soil behaves differently than dry. Rocky soil requires different blade angles than sandy soil. You're maintaining consistency. Every pass must match the previous pass within millimeters, or the road develops waves that become permanent once paved. You're working to invisible standards. Grade stakes show where the surface should end up, but how you get there is entirely up to your judgment. Do you take it in multiple shallow passes or fewer deeper cuts? Do you windrow the material to the side or blend it into the finished surface? These decisions happen continuously, often multiple times per minute, and the wrong choice becomes visible immediately in the finished grade. Could you imagine making 100 interconnected decisions per minute, every minute, for an 8-hour shift? Well, knowing that a single mistake creates problems that might not appear until the final paving crew arrives weeks later? Veteran operators talk about feeling the blade through the controls. The hydraulics provide feedback: resistance when the blade loads up with material, lightness when it's cutting too shallow. Good operators learn to read this feedback unconsciously, making constant micro-adjustments to maintain perfect cutting depth. They develop spatial awareness that borders on supernatural. They can place the blade edge within an inch of a utility line they can't see. They can grade a curve so the road surface blends seamlessly into the straight sections on either side. They can work in zero visibility: dust storm, snow, darkness, using nothing but the feel of the machine and their memory of the terrain. That the military recognized this during World War II. Combat engineers needed to build airfields in days, sometimes under fire. The Caterpillar number. 12 degrees became standard equipment for airfield construction. These machines graded runways in the Pacific, in North Africa, in Europe. Operators worked 18-hour shifts, often by feel alone since blackout conditions prevented lights. The number 12 became legendary for reliability. A single machine could grade a 5,000-foot runway in 48 hours if the operator knew their job. Maintenance consisted of greasing fittings and changing oil. The machine would run until the engine seized, and then the crew would swap in a new engine and keep grading. Some number 12s built during the war remained in service until the 1990s, 50 years later, still doing the same job they were designed for. But even as motor graders became indispensable, they remained analog machines. Every adjustment was manual. Operators used grade stakes, wooden stakes driven at measured intervals showing the target elevation. They'd check their work constantly, cutting a section, then walking it with a hand level to verify the grade. An expert operator could hold a 1% slope over a quarter mile, but 1% is roughly 50 feet per mile. Maintaining that across varying terrain, through cuts and fills, around curves, it required constant vigilance and years of experience. The industry accepted this limitation. Precision was bounded by human perception and the physical limits of mechanical controls. Then GPS changed everything. The transformation began in the 1990s with early laser-based grade control systems. A laser transmitter would be set up to project a rotating reference plane. The grader carried a receiver mounted on a mast. As the blade moved through the laser plane, the receiver measured the offset from the reference and automatically adjusted blade height. It was revolutionary and severely limited. Lasers only worked line of sight and couldn't handle complex surfaces with varying slopes. GPS eliminated both constraints. Modern GPS-based grade control works through a network of ground reference stations receiving signals from GPS satellites. These stations calculate their exact positions to millimeter precision and broadcast correction data. The grader carries GPS receivers mounted on the blade and on the cab. Sophisticated software compares the current blade position with a 3D digital model of the desired finished surface, a model that might contain thousands of individual surface definitions, varying slopes, transitions, and drainage features. The system updates blade position 20 times per second. As the operator drives, the system continuously adjusts blade height hydraulically to match the model. The operator controls direction and speed. The system controls blade height to tolerances of 3 millimeters, about the thickness of 2 credit cards. Stop and think about that for a second. A machine weighing 62,000 pounds, moving at 5 miles per hour through variable soil conditions, cutting through compacted gravel one moment and soft clay the next, is maintaining blade position to 3 millimeters vertical accuracy. That's precision you'd expect from a machine tool in a climate-controlled factory, not from earth-moving equipment working in mud, dust, rain, and temperature swings of 60 degrees between morning and afternoon. The Topcon, Trimble, and Leica systems that dominate the market cost between $40,000 and $80,000 installed. They require initial setup and calibration that can take hours. The reference stations must be positioned with survey-grade accuracy. The 3D model must be created from engineering drawings and loaded into the system. But once operational, the productivity gains are staggering. Without GPS, an experienced operator might complete 500 feet of finish grade per hour, stopping frequently to check stakes, verify elevations with a hand level, and manually adjust the blade. With GPS, that same operator can finish 2,000 feet per hour at higher accuracy, never stopping to check. The machine does the micro adjustments that previously required constant human attention and periodic verification. But here's the critical point, and why grader operators aren't being replaced by automation. GPS handles one dimension. The operator still controls everything else. A GPS system knows where the blade should be vertically. It doesn't know that there's a buried utility 4 feet to the left. It doesn't know that the material just changed from gravel to clay and the blade angle needs adjustment to prevent loading up. It doesn't know that there's a low spot ahead that needs extra fill, or that the supply trucks are running behind schedule, so the operator should adjust their pattern to conserve material. These decisions require judgment, experience, and real-time problem-solving that no automation system has replicated. The modern motor grader has become something extraordinary, a hybrid of machine precision and human judgment. The Caterpillar 24M, the largest production motor grader, weighs 62,000 pounds. The blade is 24 feet wide. The 6-wheel drive system delivers power to all wheels independently. The articulated frame can angle the front section up to 25 degrees from the rear section, allowing the machine to track one direction while the blade works at an angle. The cab is climate-controlled, with ergonomic controls and computer displays showing blade position, GPS accuracy, fuel consumption, and system diagnostics. And sitting in that cab is a human operator, making 100 decisions per minute, because for all the technology, nobody has figured out how to replace the judgment that comes from experience. The best grader operators are aging out of the workforce. The average age is 55 and rising. Young operators are scarce because the learning curve is measured in years, not months, and construction companies want immediate productivity. A construction company can put a new bulldozer operator to work moving dirt profitably within weeks. A new grader operator won't be trusted with finish work for years, and finish work is where graders earn their keep. Rough grading can be done with bulldozers and scrapers. Finish grading requires a grader and requires skill. Training programs struggle to compress decades of skill development into classroom instruction. You can teach the controls in a day, you can explain the circle mechanism in an hour. But teaching judgment, when to take another pass, how to read material changes, how to maintain grade through transitions, that comes only from experience. Simulator training helps with basic controls, but can't replicate the feel of the blade loading up or the sound of gravel under the mold board. Apprenticeship programs require master operators willing to mentor, and master operators are busy running graders on tight schedules. The industry is caught in a bind. They need experienced operators, but creating experienced operators requires years of paid training with expensive equipment. GPS has paradoxically made the problem worse. New operators become dependent on the automation for basic blade control and never develop the feel that veterans possess. They learn to drive the grader and let GPS control the blade. When GPS fails, and it does fail, from satellite outages to site-specific interference from nearby metallic structures to signal blocking and deep cuts, operators who learned on GPS-equipped machines often can't grade without it. They never learned to read stakes. They never developed blade control feel. They're helpless without the technology. Veterans who learned on mechanical graders before GPS regard this with a mixture of scorn and concern. Scorn because it represents dependency on technology. Concern because those veterans are retiring and taking their knowledge with them. The industry is facing a genuine skills crisis. The machines have never been better. The technology has never been more capable. The operators have never been scarcer. What remains is a machine that represents something rare in modern construction. Irreducible complexity requiring human mastery. A grader can't be simplified away. The work requires precision, but precision in service of judgment, knowing when to cut deeper, when to feather the blade, when to make another pass, and when to move on. Automation can assist. It cannot replace. The grader endures as a reminder that some skills cannot be programmed, some judgments cannot be algorithmic, and some machines need a human touch even when computers do the measuring. If stories like this move you, if you appreciate the engineering and skill behind the machines that built our world, consider subscribing. We explore the forgotten history and surprising complexity of industrial equipment that shaped modern life, when the motor grader went from horse-drawn blade to millimeter precision in 140 years. The journey reflects American infrastructure development itself, from dirt roads connecting farmsteads to interstate highways spanning continents. Every mile of paved road passed beneath a grader blade. Every runway, every rail bed, every precisely graded surface that makes modern transportation possible exists because someone mastered the violin of heavy equipment. The machine evolved. The skill remains. And the humans who possess that skill remain as essential today as they were when J.D. Adams first tilted a blade and changed road building forever.